All I want to look at here is I want to discuss a couple of special trigonometric functions that exist relating to sine, cos and tan, but written using a slightly different format. Now these three trig functions come into play quite a lot at advanced higher. We start to bring them into a lot more calculations that we use, so we need to know where they come from and what they represent. But not only that, we need to know how to calculate derivatives of them using the techniques discussed. The three special functions are cosec x, sec x and cotangent of x. And I'm going to show you what each of them looks like and how we can calculate derivatives of all three of them as well. First one I want to look at is sec x. Now sec x is the special name which we're going to use for 1 over cos x. So that's what this function is the equivalent of. Sec x equals 1 over cos x. And if you wanted to plot sec x, this is what the graph looks like here. Now you'll notice I've marked on 90 all the way up to 360 and I've gone back the way to negative 360. Again, as with cosine, it's a repetitive style function, symmetric here about the y-axis. There is a big difference though. Because it's 1 over cos x, we know that there are zeros every pi by 2 for cos, which means at every single pi by 2, what we're going to end up with is a vertical asymptote here because we can't divide by 0 at that point. So we're going to end up with vertical asymptotes occurring here. What we also notice is that we've got a horizontal asymptote at negative 1 and 1. Now the reason being, these occur every single pi. So we've got 0, pi, 2 pi, 3 pi, etc. The reason being, at pi, cos pi is equal to 1, which means that this will essentially be 1 over 1, which will be the equivalent of 1. As we move further in this direction here, the value of cosine gets less, which means that we're doing 1 divided by a value smaller than previously, and if we divide by a smaller number, it actually makes the overall value bigger. So instead of coming down the way as the cosine would, because cosine decreases, 1 divided by cosine increases. So it heads up that way. And that explains the general shape there. And it's actually the same logic here, the only difference being that it's negative values we have. Because they're negative values between pi over 2 and 3 pi by 2, we're going to get negative graphs at this point. So this is why it looks here. The magnitude increases, but it's a negative value. So there's the first of the three special functions, sec x. The second one is cosec x. Now cosec x is given by 1 over sine x. So it has a similar format to sec x, the only difference being this one uses sine rather than cosine. Now again, if you look here, this is the graph of this one. And again, we see vertical asymptotes and horizontal asymptotes. Now, the horizontal asymptotes at 1 and negative 1 follow the same logic as they did with the cosine. At pi over 2, 3 pi by 2, we get the maximum and minimum values of sine. As we move either side of it, the sine decreases, which means that we're dividing by a smaller number, so the overall value is going to increase and go up this way. And again, it's the same logic here, but it's just negative values. So that's why it has a similar shape to cosine. It's just slightly offset because the maximum value of sine occurs pi by 2 higher than the maximum value of cos. And again, our vertical asymptotes are at 0, pi, 2 pi, and continuing on that way because at 0, pi, 2 pi, and every other whole number times pi, what we get for sine of that is 0. So because sine of that is 0, we're going to end up with a vertical asymptote there. So that's our second special function, cosec x. Our third one is cotan of x, which in this case is the equivalent of 1 over tan x. Now the graph of cotan x looks something like this. So again with this one, we've got vertical asymptotes which occur, this time every single pi, but we have no horizontal asymptotes for this one. Now think about comparing this to tan x. Now tan comes along this direction and has this general shape and heads off up with a vertical asymptote every pi over 2. Now this doesn't occur in this one. The reason being is because cotan x is equal to 1 over tan x, tan is normally sine over cos. So that means that every single pi by 2, we're dividing by 0, so we get a vertical asymptote. Well, in this case, 1 over tan x is cos x over sine x. And every single sine function has a 0 at 0, pi, 2 pi, so every whole number times pi. So that's why, instead of the vertical asymptote occurring at pi over 2, they occur at 0, pi, 2 pi, etc. and continuing on from there. We also have a reverse of the shape of this one, because as we continue up towards pi, what's going to happen is when we do the division here, the size of the division is going to end up getting smaller because the value of cosine will be coming down, heading towards pi over 2, but the value of sine gets bigger. So the sine dominates, so what that means is that we're going to get a smaller value here. So it's going to tend towards 0 as we get to that point. Then beyond pi over 2, the value of sine starts to decrease, but the magnitude of the cosine increases, the only difference being it's negative, which is why, as we go from pi over 2 to pi, the curve heads off this way in terms of magnitude, but in the negative direction. So it's almost like a reflection of tangent of x in the y-axis and then shifted along a little bit. So that there is our cotan of x. So all 6 of our trig functions that we're going to work with are displayed here. So we've got sine x, cosec x, its corresponding function, cosine x, and sec x, they correspond together, and tan x and cotan of x and their graphs, which all correspond together. Now, one key thing we have to be able to do is calculate derivatives of each of these, using the forms that involve sine, cos, and tan, and we have to be able to simplify them as much as we can. We need to remember how to do this for when we are working through parts that are going to involve these special trig functions. So let's look at each of these in turn. So let's imagine I want to do the derivative of cosec. Now cosec x we know is equal to 1 over sine x. So if this is what my y is, then my derivative, d by dx of cosec x, what I can do to calculate that is use the quotient rule. So using the quotient rule, there's my f on top, and there's my g there. So remember, it's f dash g, take away g dashed f, all over g squared. So f dash, derivative of 1, well that's 0, so it's going to be 0 times sine x, so it's going to be 0. Take away f, which is the 1, times the derivative of sine, and the derivative of sine is cos x, and that's then going to be all over sine squared x. So what that's going to then give me is minus cos x over sine squared x. Now that looks quite nice, but we want to write it in as simple a form as possible. Well, if we look at that, what I can do is split that up to be negative 1 over sine x times cos x over sine x. So I can split it up using that fact there. What that then does is that then allows me to write it in a much simpler form. All I have to do is use these to substitute in my special trig functions, so my sec, my cosec, and my cotan, and I can write it out. So 1 over sine x, what we know is that that's cosec x, so that's then going to be negative cosec x, and we know that cos x over sine x is the equivalent of 1 over tan, so it's cot x. So what I can then say is the derivative of cosec x is negative cosec x cot x. We can remember that and use it when we're doing calculations, but this is also how we're able to prove it. Let's look at sec x. Now sec x, I know, is the equivalent of 1 over cos x. And again, I can use the quotient rule to take the derivative of this and see what we get. So the top we're going to call f, and the bottom, again as usual, we'll call g. So what I know is that if I do d by dx of sec x, that's going to be the equivalent of f dash g. Well again, f is 1, so derivative of f, f dash is 0. So that's going to be 0, take away 1 times the derivative of g. Derivative of cos x is negative sine x. And that's then going to be all over the g squared, So all over cos squared x. So this top line we can simplify. We've got 0 take away -1 sine x, so minus minus becomes a plus. So that then equals sine x over cos squared x. Now, we can use the same logic as we did before to split this off, and what I'm able to do is write that as 1 over cos x times sine x over cos x. We know that 1 over cos x, well, that's our original function sec x, and we know that sine x over cos x is tan x. So I know then that the derivative of sec x is the equivalent of sec x tan x. Final one is cot x, or cotangent of x. So we know that that's the same as 1 over tan x, which is the equivalent, with tan being sine over cos x over sine x. So there's no 1 on the top, so it's not going to be quite as straightforward as before, but we can still do it using the quotient rule. So my top line is going to be f, my bottom line is going to be g, and I'm just going to write f dashed and g dashed over here. So if f is cos x, I know that f dashed is minus sine x, and if sine x is my g, I know that my g dashed is cos x. So what I can now do is plug this all together and say fine, so my d by dx of cot x, I can use the quotient rule again to do it. So I've got f dash g, so I've got minus sine x times sine x. Take away g dashed f, so take away cos x times cos x, all over g squared, all over sine squared x. So the top, this here becomes minus sine squared x. So I've got minus sine squared x. I've got here minus cos squared x, so what I'm going to do is take the minus out as a common factor, and I can change it to minus bracket sine squared x plus cos squared x. And that's then all over sine squared x. Now cos squared plus sine squared we know is equal to 1, so it's going to be negative 1 over sine squared x. Now we know that 1 over sine x is cosec x, so 1 over sine squared is cosec squared x. So that then means I can rewrite that as negative cosec squared x. So there you go, I've got that derivative there. So I now know the derivatives of cosec x, sec x, and cot x, and how to go about calculating them all using the quotient rule. We need to be aware of these functions, aware of these derivatives, so that we can use them when we start applying differentiation and trig functions to various topics.